In 8.1, we're going to look at polynomial functions. And we've already touched on a little bit of these ideas before, so I'm just going to remind you of some of them before we begin. But a polynomial function, say p of x, is some coefficient a n, this is just a placeholder, x to the power of n. And n represents the position, plus a n minus 1 position, power n minus 1, dot, 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 all the way down to a1, x1, a0, x0. And so all polynomials function like this, and there are some that are just this last piece, and there are some that are 20 pieces long. And in the case of 20 pieces long, this coefficient could be 2, but that would be the a20th position. So it would be the a20 would be 2, and then the power would be 20. So that's kind of how you read this. So I'm looking at some examples of things we've seen in the past. Constant, linear, quadratic, cubic, quartic, things like that we've seen before. An example of a constant would just be a number. The degree is 0, the leading term is 5, and the leading coefficient is 5. Those have to stay the same because there's nothing but 5. How about 6x minus 5? Degree is 1 because it's linear function, so it has power of 1. The leading term, 6x, the leading coefficient, just 6. Okay, so leading term is that entire piece, the coefficient is just the number in front. And we'll just do quadratic here, 2x squared minus 5x plus 7. The power, or the degree, the highest degree, 2. The leading term, 2x squared. And lastly, the coefficient, the leading coefficient is 2. So this has just been kind of a quick reminder of what these are. Now I'm going to talk a little bit about whether it's linear, quadratic, cubic, what those functions in general look like. Now, one of the interesting characteristics of polynomials is this idea of the leading term. And this leading term affects how the graph is shaped. And so what we're going to do here is we're going to look at something called the leading term test, where basically what we're doing is we're asking, what is the leading term? And if it is this or that, there's two options, then it looks like these on the left or these on the right. And so it turns out that if the end pieces of our polynomial are facing both up or both down, that it's an even function. It's an even function. And if our pieces are going in opposite directions, that it's an odd function. Okay? And so we have that a to the n, x to the n, where n is even, looks like this. A n x to the n, where n is odd, looks like these. Okay, but I'm going to add one more step to this so we can even tell which way things are pointing. So for even, that's the power. If the power here is even, then we're going to have an even function. However, what if a is positive and negative? That gives us two options. So I'll start with negative a. The graph is going to open downward. Positive a, the graph is going to open upward. Okay? So n being even gives us that both ends point the same direction. A being negative means they both point down. A being positive means they both point up. Now, you could have a bunch of different jagged pieces in the middle. The middle doesn't matter. We're just talking about the end pieces. Okay, for odd, if I have negative a, it's going to start in the top left and go down to the top right. Now, once again, there could be many curves in the middle. And if a is positive, it does the opposite of this. It starts in the bottom left and makes its way up to the top right. So this leading term gives us a lot of information. It tells us about the end behavior of polynomials. As x goes to the right or as x goes to the left, what is the end of the function going to do? Are they both going to go down? Are they both going to go up? Is the one on the left going to go up and the one on the right going to go down? Or is the one on the left going to go down and the one on the right going to go up? Now, one of the biggest things that we want to do with polynomials is not just talk about their end behavior, is we also want to talk about the zeros or the solutions to the problem. Now, the most simple way to find solutions is by graphing. So you have a function and you graph the function, you see where it crosses the axis. However, we may not always have that option, and it's good to understand how the computer is calculating those values. So what we want to do here is we want to look at a few examples. So how about x, if I say y of x equals x cubed plus x squared minus 17x plus 15. Okay, and I'll go ahead and just change this to p of x, which I was saying a second ago. So if I have this function here and I want to test if something is a zero, then I have to just plug it in. If I ask, is x equal to 2 a zero for this function, I just plug 2 in, and what should my value be when for y be whenever I get my result? They're called zeros for a reason. My y value should be equal to 0. So let's plug 2 in and see what happens. 2 cubed plus 2 squared minus 17 times 2 plus 15. Okay, well this is 8 plus 4 minus 34 plus 15. 12 and 15 is 12, 5, 2, 7, 27 minus 34, negative 7. So is 2 a 0 for this function? No, it's not, because we didn't get 0. Whenever I did p of 2, I did not get 0. So it is not a 0 for this function. Now there are some, matter of fact there are 3, because the power is 3, but in this case I'm not going to go any further with this problem. Okay, so remember, in order to find the zeros, we set each piece to 0. So x minus 2, x minus 2, x minus 2, and x plus 1. But since these 3 are the same, they're all going to give me x equal what? 2. Remember, x minus 2 equals 0. Add 2 to both sides. Same thing here, subtract the 1. So x equals 2 and negative 1. Okay, now this is the cool part. I can actually graph the function with just knowing these two things. What is the total power? 1, 2, 3, 4, right? So the power is 4, which means both ends are going to be pointing up. Okay, so what I'm going to do first is I'm going to put a mark at negative 1 and a mark at 2. Negative 1 and 2, my zeros. Okay, this 5 here tells me they both are open upward because A is positive. So I got my power from 1, 2, 3, 4, and I got my positive A from here. So that tells me this end is going to go up, and this end's going to go up. Now, something I didn't mention earlier, but I will now, since all 3 of these have the same power, there's 3 roots in that same position. So when it goes through this, it should curve through. It should curve through. If there's 1, it goes straight through. If there's 2, it bounces. So even bounces at the 0, odd curves through the 0, and 1 goes straight through the 0. And so our function should look something like this. Now, is it going to be perfect? No, but that's okay. So let's look at another example. In this example, we still have 1, 2, 3, 4, 4 power. Power is still 4, so the degree is still 4. I'll just put, no, I should, DE for degree, is 4. Okay, so that tells me that the ends, and it's positive, so it says that the ends should look like this. Okay, we don't know about the middle yet. We're going to find that. So if I set x minus 1 to 0, I get x equals 1. If I set x plus 2 to 0, I get negative 2. Now, there are 2 of these and 2 of these. So what should I do? I'm gonna mark down negative 2. I'm going to mark down positive 1. Now, I know from this that both ends go up, because positive, and there are 4 of them. So power of 4 means same direction. Positive means up, not down. And then, because there are 2, at that point, I'm going to bounce. And 2 at this point, I'm going to bounce. And so it looks like that. So you can see what I meant a second ago when I said cubic. If there's 3 pieces at a point, it kind of curves through. 1 piece at a point, it goes straight through. 2 pieces at a point, it bounces. Okay, and that's always true. Okay, now we have learned a method of factoring when we have 4 pieces, factor by grouping. So let's group the first 2, group the last 2, and see if we can't get anything in common. So the first 2, what do they have in common? Well, they only have x squared in common. What's left? X minus 2. Okay, what do these 2 things have in common? We know this has to be minus right here. So I need this to be negative, so I have to factor out a negative 9. And what's left? X minus 2. So now we have 2 pieces. X minus 2, x squared minus 9. Okay, but we also know that x squared minus 9 is the difference of squares. So that's x minus 2, x plus 3, x minus 3. Remember, the square root of this goes in both, and then it becomes positive, negative when we have difference of squares. Now, where are my zeros? 2, negative 3, and 3. So I have 3 in this case. 1, 2, 3. 1, 2, 3. Now, what was the power? What was the degree? I'm sorry. 3. And is this positive or negative in front? It's positive in front. So it's going to start, positive A in front does this for odd functions. Okay? So I should expect it to go up here and down here. Now, is this a single point by itself? If so, then we go through. Is this a single point? Yeah, so we go through. Is this a single point? Yeah, so we go through, and then we connect. And so our graph should look something like this. Now, once again, my drawings are not perfect, but that's the idea here. We can take the power and the A and find the zeros and get a good picture of what the graph will look like. This function represents milligrams of ibuprofen in a person's system after a certain number of hours. Now, it is conditioned based on the fact that they took 400 to begin with. So we have a condition starting amount is 400 milligrams. And T is time in hours. Okay? So if I asked you how many milligrams of ibuprofen are in someone's system after 3 hours, then what would you do? Well, you would say T equals 3, and then plug 3 in for T, and spit back an answer saying that M of 3 equals, I've got it right here, 306.9. 306.9. So, this is an example of how polynomial functions can be used. Now, this does have a second condition. Sorry, that's condition number 1. Condition number 2 is that t is less than 6. So after 6, this function is not applicable anymore. It doesn't correctly tell the information we want after time of 6. So if I ask you, find time of 0.5, time of 1, time of 5.5. So find those 3 things. Pause the video real quick, and then I'll put the answers here and you can see them. So you can just plug this in somewhere and plug in these values. That's all you have to do. And so at 1/2 an hour, m of 0.5 equals 150.2. M of 1 hour equals 255. M of 5.5 equals 20.2. Okay? And so polynomial functions are great for modeling as long as the model fits the data. And so there's a lot of examples out there where there's data scattered everywhere on a graph. I'll make one real quick. They have data. Okay, and what you're attempting to do with modeling is you're attempting to say, well, what's the best fit line? Is that the best fit line? Or is that the best fit line? Or is that the best fit line? Or is something like that the best fit line? And so what you're trying to do is figure out how to model the data with these polynomial functions. And once you are successful in getting a model that you think is accurate enough, then you can develop something like this, where we say, hey, plug in a number, it'll tell you how many milligrams of caffeine are in, or sorry, milligrams of ibuprofen are in your system after a certain amount of time. So that's kind of where this stuff comes from, is there's tons of data that's taken. They try to best fit lines through the data, and there's all sorts of statistical programs that can help you do that. And then once you have that information, then you can begin to develop models that are more and more useful.